All right, guys. Hey, so this is going to be a little bit of a longer lesson. I think I'm going to break this up into sections here. So this will be multiple videos for these notes that I handed out. The first couple videos are going to be on a little bit of a review. Just wanted to kind of fill in some gaps that I feel we're missing when we're talking about work, energy, power, and efficiency. All right. So a little bit of this review. Some of this will be a little bit new. All right. So you see that work is defined as transfer of energy, which we've talked about, right? In its simplest form, we know that work is equal to change in energy, right? In order to do anything, right, we move an object from point A to point B, right? We need energy, and we use energy to move objects, right? And by doing that, we are doing work. More specifically, right, we can expand that out to work equaling force times distance. Remembering that our unit for force is newtons, our unit for distance is meters, so the unit for work is Newton meters, which is also the same as joules. Now, we'll get into torque very shortly, and we'll see that these are the same units. The only distance or difference here is we're going to be talking about different quantities. All right, go ahead and pause the video. We have a couple example problems here. So pause the video now to work on example 1 and example 2. All right, and then you can continue the video, and I'll kind of show you how we would break this down. So for example 1, how much work is required to lift a 2-kilogram textbook from the floor to a height of 1.5 meters at constant velocity? All right, we can visualize that problem. So our textbook, gravity, we're applying a force upwards. All right. And we're doing this at a constant velocity, which means that our applied force is going to equal gravity. All right. So we know that our force, in this case, is going to be gravitational force, which means that this is expanded out to mass times gravity times distance. And then from here, just plug and play. Right. We know that our mass of our book is 2. Gravity is 9.8. And then distance or displacement was 1.5. And then add this all up, or multiply it, about 29.4 joules. All right, since the velocity is constant, what's the net force acting on the book? Again, net force, obviously, if they are balanced, really should go without saying. Net force is 0 newtons. Example 2. How much work is done on a 4-kilogram medicine ball that's held at a height of 1.8 meters for 10 seconds? So once again, notice that our object is still moving with constant velocity, even if it is not moving. So our forces in this case are balanced as well. Now, key thing we know, right? We kind of did this at the beginning of our unit. If you just hold something out, your arm will get tired, right? That's because you are using energy. So is energy being used? Yes. Right? You are physically using energy. Is work being done on the ball? No. Right? Because in this case, the distance is 0. All right, so right, when we're plugging this into our formula, if we have 0 within our equation, then the work is 0. All right, let's get a little more complex here. Right, we now have a force acting at an angle. So he is pulling his sled at a constant velocity of 1.2 meters per second, pulling a 15-kilogram sled, force of 35 newtons at a 40-degree angle to horizontal. How much work is he doing to pull it 20 meters? All right, again, helps here to draw our free body diagram. Got friction. All right. And here's the key piece. Right? We have our force applied, and we can break this down into two components. All right, our X and Y components. So we have force in the Y direction, force in the X direction. Now we know here that we are focused on the force in the X direction when we're talking about work. And we've introduced this before, but we could expand out our formula to be force equals, or work equals force times distance cosine theta. So if we add this out, right, our force is 35, our distance is 20, and the angle is 40. So work done in this case is 536 joules. All right. Now, key thing here, we are pulling this in the X direction. We're not pulling it in the Y direction. So while there is some force pulling it in the Y direction, right, this is not the direction that we are moving our object. So does the vertical component of the force do any work? The answer is no. Because in the Y direction, the displacement is 0. Okay. So when finding the work done on an object, we only consider the component of force in the direction of the motion. All right, so we can expand out our formula to be force in the direction that the work is being done. All right, one more example problem here. Pause your video. All right. When you're ready, we'll begin again. So, quick reminder. So remember, work is defined by what force you apply on the system. So in this example, we have a biology student pushing a rope 15 meters across a flat surface. Student pushes the rope with a force of 220 newtons, while the force of friction is 120. How much work is the force doing? All right, to find the amount of work done by students, should we use the net force or the applied force? So again, right, our work is defined by what force we apply on the system. So, right, we are using the applied force in this case. So our work in this case is defined as the applied force times distance. All right, we can ignore that frictional force because we don't use the net force. Plug in our force and our distance, and get 3,300 joules. So when we're finding the total work done on an object, we always use the force applied. All right. Now notice that work is a product of a scalar and a vector, but work specifically is a scalar. All right, we just define work as a scalar, so just its magnitude. Just like energy, right? All right, now work, different than others, can be positive or negative. So for these 4 examples, I want you guys to just indicate, is this a case where work is going to be positive or is it going to be negative? So pause, write out your positive negatives. You could just use plus negative signs to indicate, and I'll show you here. Okay, 3, 2, 1. Car accelerates from rest, positive work. Skater stops suddenly, negative work. Lifting an object above your head, positive work. Ball rolls down a ramp, positive work. All right. So we've been talking a lot about stored or different types of energy. Again, just going to go over this real quick. Potential energy we define as stored energy. Right. Now we're talking about our gravitational energy. So this could be PE or UG. See, written a couple different ways. Right. Potential energy is always relative to a reference point. Right. So we're talking about the height or the change in y. Right. We're talking about from where. Where is that height starting from? It's not always going to be necessarily the surface of the Earth. All right, kinetic energy. Where this is the energy of motion, or energy in motion. This could be EK. It's 1/2 mass velocity squared. Again, you can go ahead and derive that. See, it's derived from the side, and that's going to be useful as we move through this. All right. So I want you guys to take a look at this example 6, the work energy theorem for net force. Go ahead and we just want to do a couple things to kind of define this. So it's worth noting that the work done by the net force on an object is going to be equal to the change in kinetic energy. So remember, work done by the net force this is a portion of the total work. So here, let's define this. All right. Work is equal to net force times distance, which we could expand out to being work is equal to mass times acceleration times distance. Now, this is kind of where the deriving this formula on our previous page comes in handy. So let's focus on this part of the equation, acceleration times distance. Right. If we go back to our kinematic equations, one of them is the equation for final velocity squared. Which looks like this. Final velocity squared equals initial velocity squared plus 2 times acceleration times distance. If we solve for acceleration distance, we get 1/2 final velocity minus initial velocity squared. Right? Which means we can then plug this in back into our formula. Where we get work equals 1/2 mass times velocity squared minus initial velocity squared. Another way to say that would be work is equal to 1/2 mass change in velocity squared, which is equal to the change in kinetic energy, which, going back to the beginning, is equal to net force times distance, or displacement. All right. example problem here. Again, pause. You can use this to help you solve. All right. Playing it again. All right, so we have a 1,270 kilogram car accelerating from 15 meters per second to 25 meters per second over a distance of 75 meters. Determine the average net force that was required to do this. All right, we just applied a new formula here. So we know that our change in kinetic energy is equal to our net force times displacement. To rearrange this to be net force is equal to our change in kinetic energy over displacement, which again we can define as being equal to our kinetic energy formula. So we end up with net force equals 1/2 mass velocity squared over displacement. Use that formula to plug in our known variables. So our mass is 1,270. We have our change in velocity squared. So our final is 25 squared minus 15 squared all over 75. Plug that all into your calculator, and we get 3,390 newtons. Now, when we're graphing force by distance, right, this graph is going to show us the total amount of work done, which is going to be helpful. Right. Now, again, when we're talking about graphing, we can kind of break this down into the area between our curve and the x-axis. So we have a few shapes here. You can break this down. I just cut off there. All right, so we're trying to find the total amount of work done. So let's call this area 1, area 2, area 3, A4, and I suppose A5. All right. And our goal here is to determine size of the area. Keep track of your positive and negatives, right? Because work can be negative. A1, 2 times 20, half. A2. 4 times 20, 80. 3, 4. So A, total work. Add it all up, 100, 140, 170. And for B, remember that work is going to be our change in kinetic energy. So we're trying to find the final speed, so final velocity. change, right? We know in this case, the initial kinetic energy is going to be 0. So really we're just trying to find the final. As we've done before, we've derived velocity, which is equal to 2 times the work done divided by the mass. Right, and then use that to solve. Right. So we do the square root of 2 times 70 divided by 15. I need my calculator. Sorry, I'm going to pause so you guys can solve it. It's going to be 3 something. Okay. 3.05, we'll say. Now, so let's do a quick summary here. Our work total is the same as the change in our energy, or total energy, which is equal to the applied force times displacement. Our change in kinetic energy is equal to our net force times displacement. And this is not really going to be necessary, but is helpful. Our change in thermal energy indicate that up here, is going to be our frictional force times distance, or displacement. Right. Moving on to law of conservation of energy. We know that energy cannot be created or destroyed, only changed from one form to another. Therefore, if only our conservative forces act in the system, the total change in energy is always 0. So if it's a closed system, so our total initial energy, or E sub I, equals our final energy, or E sub F. We can expand that out to be our initial kinetic plus our initial potential equals our final kinetic plus our final potential. Right. So it's going to be expanded out even further. 1/2 mass times velocity squared initial plus mgh initial equals 1/2 mv squared final plus mgh final. Now we know that our total change in energy is going to be 0, so our change in kinetic energy plus our change in potential energy is going to equal 0, which means that our total change in kinetic energy is equal to a negative potential energy. All right, we can pause to solve this problem. We did a similar one already. All right. So we have a roller coaster. The total height of it is 55 meters. All right. Kind of broken up into two little hills here. All right, so we have our cart at the top of one. All right, it's going to start from rest, go down the hill, and then up a second hill, which is 30 meters high. Our goal is to find out how fast is the car traveling at the top of the second hill. Now, I've done a problem like this previously. And there are a couple of different ways we could solve it. So I'd like you guys to pause, solve it on your own. All right, and we're back. All right, again, we can use one of our expanded formulas. All right, we know that our initial potential plus our initial kinetic equals the final versions of each. Again, what we can do, right, remember potential energy is from a reference point, so we can use this red reference point here to kind of represent our zero. So what we do then is we know that at the very beginning of the roller coaster, right, there is no kinetic energy. And we know at the end, if we consider the red line to be zero, or a height of zero, then we know that at the time it's at the second hill, it has no potential energy. What that means is that our initial potential is going to equal our final kinetic. Expand it out, that means our initial mgh equals 1/2 mass velocity squared. And then before plugging anything in, we can simplify this. We see that our masses cancel. And then we are solving for final velocity. So put this all together, we get final velocity equals square root of 2 times gravity times the initial height. Again, the initial height is not 55 meters, it's 25 because we're based off that red reference point. So we get VF equals square root of 2 times 9.8 times 25, square root it all, equals about 22 meters per second. All right, I'm just going to finish up this little lesson here. So, not necessarily in 11th grade, but in a previous physics class, you guys may have learned this, right? We're talking about non-conservative forces, such as friction, right? Forces that will take away energy from our system. This is just reality, right? There's, in our perfect world problems, everything's going to be equal, but they are not always because of the real world, right? There is air resistance, unfortunately, in the real world. Anyways. All right, the work done by friction does produce a form of energy known as heat or thermal. Thermal energy. All right, we know that thermal energy is conducted, convected, radiated, and then just kind of disperses into our air. So if we have a wood block sliding down a ramp, there's going to be friction. Right? So we think about how would the block's kinetic energy at the bottom compare to its potential energy at the top, right? In the real world, would it be completely equal? And then why? Right, in the real world, right, the initial potential energy is not going to fully equal the final kinetic energy, right? It is going to be greater. And this is because some of our potential energy gets converted or lost as thermal energy. So the fact that the amount of energy in the block decreases slide down the ramp does not disprove the law of conservation of energy. In fact, it just shows that the total energy in the system is constant, right? It just changes forms. So this is not necessarily going to be something that will be applicable to this particular AP exam, but we can, just for the real world sake, since hopefully you guys are going to be using physics and engineering in the real world, right? We'd have to consider that with our initial formulas, right? The initial kinetic plus the initial potential is going to be equal to the initial kinetic plus, the final kinetic plus the final potential plus thermal energy. All right. And then the change in each altogether is still going to equal 0. Okay. You can pause to wrap up this example problem, and then I'm going to end this video before getting into the next set of notes. So pause for a sec, solve, and then we'll go over the answer. All right, so the wood block, it's pushed down with an initial velocity of 6 meters per second. Excuse me. By the time it gets to the bottom, it increases velocity to 7.5 meters per second. Our question here is determining how much thermal energy is generated due to friction, and then we can also determine the force of friction. So, our goal is to determine our thermal energy. So let's break out our formulas, right? Initial kinetic plus initial potential equals final kinetic plus final potential plus thermal energy. Now, a couple things we know: when the block is at the bottom, we don't have any more potential energy. Now, again, here, what we're trying to solve for is our thermal energy. All right, so if we're isolating that, we end up with thermal energy equals the initial kinetic plus the initial potential minus the final kinetic. Expand out our formula. This shouldn't be too difficult because we're given most of the variables we need. Just ends up being a lot of numbers. Right. So plug in our numbers for our initial, right, kinetic energy at the beginning. It is moving at the beginning, so it's not going to be 0. So plug in our mass is 5. Our initial velocity is 6 squared plus, mass, gravity, height. So 5, 9.8, 1.5. Okay, and then we're subtracting, right, the kinetic energy at the bottom. So it's 1/2 times 5 times 7.5 squared. Plug this all in. Right, again, it's helpful to kind of do these each individually. And then we end up with about 23 joules of thermal energy. Remember, we defined thermal energy, or the change in thermal energy, as being the force of friction times displacement. So solving for the force of friction, we end up with change of energy over displacement. And we found that the change in energy is 22.9 joules. The displacement, right, it went 3.5 meters. Joules divided by meters, you're going to get newtons. All right. So I'm going to end the video here. I'll do a couple more videos for the next couple lessons, but this is a good time to take a break.